Ginkgolides are biologically active terpenic lactones present in ginkgo biloba. They are diterpenoids with 20 carbon skeletons, which are biosynthesized from geranyl pyrophosphate. Ginkgolide B, specifically, is a diterpenoid trilactone with 6 5-membered rings. It contains a spiro 4 nonane carbocyclic ring, a tetrahydrofuran ring, and a very specific tert-butyl group at one of the rings, figure 1. The class of ginkgolides was first isolated from the ginkgo biloba tree in 1932. The elucidation of its structure set in 1967 by Maruyama et al., who isolated Ginkgolide B in 1967.
Background.
It is extracted from the root bark and leaves of the ginkgo biloba, ginkgo meaning silver apricot, tree found native in China. It is marketed to other countries that include Korea, France, the United States, etc. for the drug and clinical properties of the extracts. Present in the tree is less than 0.1 to 0.25% of Ginkgolide B, the most abundant being Ginkgolide A.
Clinical applications.
This class of molecules have been researched for many years due to its ability to act as an antiplatelet activating antagonist (PAF) receptor in treating cardiovascular diseases. Ginkgolide B may be effective as preventive treatment in reducing migraine attack frequency. Ginkgolide B is also used in treatment for cerebrovascular disease. Research has also proven that Ginkgolide B can also treat migraines in young ages. The literature indicates that Ginkgolide B functions as a selective antagonist of glycine receptors based on non-competitive inhibition for the neurological system that this compound performs.
Spectroscopic studies for the elucidation of the individual structures for the ginkgolides.
Ginkgolides A-C were isolated from a large-scale methanolic extraction followed by liquid-liquid partitions, column chromatography and repeated crystallizations. The molecular formulas were determined by high-resolution mass spectrometry, and the overall structures by IR and NMR spectroscopic analysis and extensive derivatization techniques.
Biosynthesis of Ginkgolide B.
While researchers have published chemical pathways to make this molecule, most of the designed syntheses were too complex and produced little of the actual material to run full analyses. Therefore, studying the biosynthesis of the molecule is preferable. Most of the natural product terpenoids start with isopentenyl diphosphate synthesized by the MEP pathway. This pathway also generates dimethylallyl diphosphate, from pyruvate and D-glyaldehyde 3-phosphate GAP. When coupled together, they form one molecule of geranyl diphosphate with geranyl diphosphate synthase. A molecule of GGPP generates 1+-capallyl in the presence of levofumaridiene synthase. A then 1 loses its OPP group catalyzed by this same synthase, performing an intramolecular allylic cyclization with the two alkenes, to form 2 the sandaricopymarinol cation. B. This cation then undergoes an internal cyclization to stabilize the carbocation in the ring by proton transfer to form 3 intermediate C. By doing this, the molecule sets itself up for a methyl migration to stabilize that secondary cation and generate that tertiary carbocation at 4 D. This induces a loss of proton to get 5 levofumaridiene E. With oxidation, a loss of a proton to form an aromatic ring generates 6 abietatriene G. This newly formed abietatriene undergoes a 1,2-alkyl shift to break the 6-membered ring into 7 with a 5-membered ring, more favorable, H. Another 1,2-alkyl shift takes place at the same time a ring cleavage takes place to generate 8. Oxidation at all the positions with alkenes generates 9 intermediate, which then undergoes ring closures featuring 1 hemiacetyl in all 3 lactones to get Ginkgolide B at 10.
See also
Bilobalide.
References